Okay, so we're here today for a quick overview of some of the topics we've learned in unsupervised learning. So we'll look at a little bit of clustering and then we'll talk about dimensionality reduction. So the clustering algorithm we've learned was k-means, and the idea behind k-means is it produces clusters by trying to minimize this distance. Okay, so here is a sum over all clusters, sum over all points in a cluster of the point and cluster mean. Okay. So this is a loss function it tries to optimize. And this is really the whole trick behind unsupervised learning. In supervised learning, it's all about how we find the prediction. And then the loss function we try to minimize is the difference between the prediction and the true value. With unsupervised learning, there is no true value to compare to. So it's not always obvious what the loss function should be. And so that's a whole innovative part of unsupervised learning, identifying what is it you want to learn and what kind of loss function you can use to actually learn that. Okay, so looking at this data, it's pretty easy to pick out 4 clusters. Right? So we can visually see that there are roughly 4 clusters of the data. And I can import the sklearn k-means clustering method. Just like all the other sklearn models we've looked at before, it supports a fit method and a predict method. So I fit it to my data, and then I can use it to predict my data, predict the cluster labels. And visually, we can see it looks like it did a pretty good job. Now, that was here in this case, but there is actually many limitations to this algorithm, so we'll look at it a little more closely. So we know that the general idea behind this algorithm is you start with some random initialization of cluster centers, for example, as here. The next step is what's known as an expectation step. So that involves updating our expectation of which cluster each point belongs to. So here you can see the next step after the random initialization is an expectation step of assigning each point to its nearest cluster. Right? Where when I say nearest cluster, I mean we find the pairwise distance between each point and each cluster center. And then we apply the label to the point according to the nearest cluster center. All right, the next step is a maximization step. The maximization step is maximizing some function that defines the location of the cluster center. So this is a general iterative process that's used for clustering, not only with k-means, but here we're looking at it in the context of k-means. So in the maximization step in k-means, you update each cluster center to just the mean of the points in the cluster. Okay, so we started with a random initialization. Then we do the expectation step where we update which cluster each point belongs to according to the nearest neighbor, nearest cluster center. Then we do the maximization step where we move each cluster center, in this case, to the mean of all the points assigned to that cluster. And then we repeat. So you can see, for example, after this maximization step, there are now many of these purple points that are very close to these yellow points and not part of the broader purple cluster. But when you do the expectation step after this, we update all the class memberships again. And then we move the cluster centers. And then we might do another round. Eventually, you can see we're no longer updating the cluster centers anymore, and we're no longer updating the cluster memberships. So that leaves us with this final cluster. Okay. It's pretty simple to actually implement this by hand, not using the sklearn k-means. So you can see this implementation here. First, we just assign random cluster positions for initialization. And you can see here that the number of clusters is also passed as an argument. So we're not finding the number of clusters. Now, after you initialize these random centers, then you loop over the rest of the process. So you loop over this expectation maximization cycle. First, you do the expectation step. You assign the labels based on closest center. So for every point, you find the pairwise distance to the point and the centers. Then you can find the new centers from the means of the points. So here for every cluster center, we're looking at all of the points that are assigned to that cluster by the previous case. And we're updating the cluster center position by the mean of the points. And then finally, if our algorithm is not changing the cluster center position, then we just stop. And you can see here's how that works on this. It found the same cluster centers. Now, this is a very, initial approach, but there are actually a lot of challenges with this method. Okay. So one obvious challenge is that it's very sensitive to initial conditions. For example, here I'm doing the same thing, okay, calling the same function up here, but I passed a different random seed. So the random seed is what determines our initial cluster position. You could see with a different initialization, the model might find totally different clusters, and here it's clearly not optimal clusters. Right? What do I mean when I say it's not optimal clusters? Well, we said we're trying to minimize this. This algorithm is not really guaranteed to minimize that. So it really all depends on the initial cluster centers. Okay. Next, we need to decide the number of clusters in advance. So that's another challenge. If we ask it to find some other number of clusters, like 6 clusters, 20 clusters, 3 clusters, it will happily do that, even if it doesn't really make sense to do that. Okay. So if we don't know the number of clusters in advance, so if we don't, let's say, know in advance, or we're not able to easily visually identify some correct number of clusters, then we need to use some other method to try and identify the number of clusters to ask the k-means algorithm to use. And there are some methods to do that. So some of these are listed here, but we're not getting into this because we have 1 week to spend on unsupervised learning. Another limitation is doesn't necessarily work well for kind of complicated cluster boundaries. So in this example, you can see that all of the clusters are well separated by, kind of pairwise separating hyperplanes, right? So you could draw a line like this separating the blue one, a line like this separating the green one. You can kind of draw, probably easier, more dimensions, but you can draw a line separating the yellow one. Not exactly, but close. But if you have some nonlinear boundary between clusters, it's much more complicated. And k-means, you can see, does not do very well with that. So here's an example of applying k-means to this half-moon data. Now, there's 2 very obvious clusters here, right? Cluster 1 and cluster 2. K-means doesn't find this. Now, this is actually a case where this loss function, right, of finding the distance between each point and the mean of the clusters, well, this loss function doesn't seem very appropriate for this particular clustering problem, right? Because here, what we'd really like is for all points in this moon to be part of this cluster, all points in this moon to be part of this cluster. It's very clear that these points are closer to this cluster mean, but that's not where they should be assigned. So this is not a problem of the algorithm not finding the optimal clusters according to this loss function. It's a problem of this particular loss function being somewhat inappropriate for this data. Now, looking at this nonlinear data, you may remember that when we've worked with nonlinear data in the past, we've had various approaches we can use to make them work with the linear method. So for example, we learned linear basis function regression or logistic regression with linear basis functions. where we can project the data into a higher dimensional space using basis functions. And then we are able to do linear separations. Or similarly, using support vector machines, we saw that we can use a kernel to work with the data in a different dimensional space where it's more easily linearly separable. So we can do actually something similar with k-means. Again, not going to get into details, but sklearn comes with a spectral clustering algorithm that's able to learn more complicated clusters. You can see from the description, when I click on it, it says that this is more appropriate when a measure of the center and spread of the cluster is not a suitable description of the cluster. So this is a great example of something like that, where the spread from the mean of the cluster is not really a good estimate of the loss. Okay? And this algorithm is able to classify these moves correctly. Another problem is that it's kind of slow for a large number of samples. So this has the same problem as k-nearest neighbor. You remember for k-nearest neighbor, we said it's very problematic to have to find distances between every point and every, let's say every new test point and every point. We have a similar problem here where as a dimensionality grows, the cost of each distance grows. And for each iteration of k-means, we have to find the distance between each cluster center and every point in the data set. So if there are many points in the data set, training can be very slow. If the dimensionality of the data is high, training can also be slow. Now, it's not nearly as problematic as k-nearest neighbors, because in k-nearest neighbors, we have to go through this entire step just to find the, just to do inference for one new point. Here, this really happens during the training process. So it's generally not as bad to have the costly training process as a costly inference, but it's still a concern that it's pretty slow. There's an alternative which does like a batch k-means, where we use only a subset of the data to update the cluster centers. Right? So when we find the cluster centers, let's say that's this point. So mini batch k-means uses a random sample of the data to update the cluster centers. And that's a little faster because it doesn't need to compute nearly as many distances. So that's an alternative if you want it to be a little faster. Now, here's an example that's a little bit interactive so that we can look through some of these issues. So here's an interactive k-nearest neighbor where we can step through the steps of the algorithm one at a time by moving this frame slider. We can change the random seed used for initialization using this initialization slider. Okay, so you can see as I change that, the center, cluster center, which is here, is initialized in a different place. Okay, we can also change the number of clusters we ask it to find. So let's run through a few examples. Okay, let's try 2 clusters. We'll use our, let's say, first random initialization. Okay, I have 2 clusters. The cluster centers are marked as like colorful circles, but with the point in the middle. So there's one here, one here. And let's step through this algorithm. So the first step was to assign the cluster centers to some random position. Next, I'm going to reassign points to the nearest cluster. So here I have a yellow cluster here, a purple cluster here. This number of points are closer to the purple cluster, and these are closer to the yellow cluster. Okay, so far so good. My next step is going to be to move the cluster centers. So where do I expect these cluster centers to move? First of all, which one is going to move more, the purple one or the yellow one? Okay, so I expect the purple one won't move much. It's already kind of almost in the center of its assigned points. The yellow one has many points to the top left, so I expect that it will move much farther to the top left. Okay, so you can see the yellow one moved right here. All right, now that we've updated cluster centers, we need to repeat the expectation step. So we're now going to go on and assign points to their nearest cluster again. Okay. So here we've assigned these points, and these points to purple, these points to yellow. You may be a little surprised at this point here, which kind of appears to be much closer to the yellow, is assigned to the purple. That's because notice that the scale of this data is not the same in both directions. So the vertical axis goes from -4 to 4. The horizontal axis goes from -2 to 10. Horizontal axis is from -4 to 4. Vertical axis is from -2 to 10. So the scale is very different. Here, since the data spans a larger space along the vertical axis, that feature, whatever it is considered much more important for the clustering. So this is a similar problem as what we've seen with, let's say, k-nearest neighbors and many others, where if you don't scale the data before you apply the model, before you train the model, then the feature with the largest span will dominate the model. Now, sometimes that's good. Sometimes it spans a larger value because it's a more important feature, and maybe you want it to dominate the model. Sometimes it's not good. Sometimes it spans a larger range because, maybe it's just measured in different units. So you have to carefully think about what the problem is and decide whether it's appropriate to scale the data or not. Sometimes if you scale the data, you kind of lose information about a feature. Sometimes if you don't scale the data, then you end up not using the most informative features just because they happen to be measured in different units. So this is something where you really have to understand what the problem is and what the data is in order to understand whether scaling is appropriate or not. Okay, let's continue with our k-means. Okay, so now we're going to update the cluster centers. You could see they're not moving as much already. Okay, next step, we'll reassign points. Okay. So you can see at this point, we've basically stopped updating anything. So we're repeating more iterations, but we're not assigning different points to cluster centers, and so their positions are not changing. And so we can say these are the final clusters for this k-means iteration. Let's try it again with a different set of initializations. Okay, so here I initialize 1 point here, 1 point here. Choose a different set. Okay, let's choose a set next. All right, so I'm still going to be working with 2 clusters. I have a purple cluster center initialized here and a yellow one initialized here. Let's step through it frame by frame. Okay, so I started by assigning points to their nearest cluster. Both of the cluster centers are going to move quite a lot this time. And you can see with this initialization, we again ended up with a very similar final clustering. But if we look at the final clustering go across all initializations, you can see they're not always the same. So here, for example, here you can see like all of these points are part of a cluster together, and these are part of a different cluster. Whereas with this initialization, all of these points are part of a cluster together, and this one is different. So the results of a cluster, not only which color is which, but also which points are in a cluster together, are very sensitive to the initialization. Let's look at an example with a kind of correct number of clusters, so 4 clusters. Okay. Let's find an example that found kind of some bad clusters. Okay. Maybe not this one. Okay. So here's an example. We randomly initialize our cluster centers as shown here. It's a little difficult to see, but I have a purple one here, a green, a yellow, and a blue one here. And let's step through it. Okay, so in our first iteration, all of these points are assigned to the purple cluster center. All of these points are assigned to the green one. Now notice that no points are assigned to the yellow or blue clusters in this iteration, because there are no points that are closer to yellow or blue centers than to any other center. Now we'll move both the green and purple centers to the mean of their clusters. In the next iteration, I expect the yellow cluster center to get a little more involved. Okay, so now you can see in the next iteration, we now have some points that are closer to the yellow cluster center than the purple. So even though the cluster centers started all grouped together over here, the yellow and green one kind of moved out. But as we repeat this algorithm, the blue one is not really moving at all. So even though we asked it to give us 3 clusters, we asked it to give us 4 clusters, and it did give us 4 clusters. You can see it's not really using 4 clusters because one of the cluster centers happened to be initialized to a location that's not very close to the data, and where all the other cluster centers are always closer to the data. So even though we asked for 4 clusters because of our poor initialization, we in practice only ended up getting 3 clusters because we have no points assigned to the blue cluster. Okay. Let's look at an example with more clusters. Okay. So sometimes if we ask it for 6 clusters, we'll get a kind of similar situation where even though we asked for 6 clusters, it only gave us 4 because the random initialization put these cluster centers somewhere where they're not very useful. But other times it might happily try and give us 6 clusters, like this example, where these 2 clusters are really, logically you can see visually looking at them that they're part of the same cluster, but the algorithm doesn't really care about that. So it's still just trying to optimize this function. And the more clusters we have, the more happily we'll optimize this function, because if you have more cluster centers, you can make each point closest to the cluster center. In the extreme, if we told it to have as many cluster centers as there was data, right? If there are 100 data points and we tell it to give us 100 clusters, it will very happily go find 100 clusters. And pending our random initialization, we may actually end up with every single point being in its own cluster and 0 error. But of course, that's not necessarily meaningful. So we could achieve 0 error on this loss function if we have as many clusters as we have data points. But obviously, that's not a meaningful metric. So there's a whole other family of algorithms that's all about, first of all, a whole family of algorithms about how to initialize the cluster means. Then there's a whole other family of algorithm that's all about how to decide how many clusters to have. And so there are many improvements on this algorithm. Now, despite that, it can still be very useful. So we're going to look at a couple of examples of using this clustering in somewhat meaningful ways. So we're going to load in our familiar handwritten digits data set, but we're going to use a small version of it. So it only has a small number of samples, and each sample is only 8 by 8. Okay, so we're using a very low resolution version of it. Okay, so 64 features instead of 28 by 28, which is what we've used in the past. Now, what we've just done after loading in this data is we've applied k-means clustering and asked it to find 10 clusters. Okay. And after we asked it to find 10 clusters, so we have a cluster center for each cluster. And each cluster center always has the same dimension as the data itself, right? As the points in the cluster. So we have 10 cluster centers, each one is 8 by 8. And here, this is a plot of the cluster centers. So we can see that even though we didn't tell k-means to do anything about like separating by by handwritten digit, right? So we didn't actually tell k-means anything about the data labels. We only gave it the feature data. So we didn't actually tell it anything about, these are 4s, these are 3s. Didn't look at feature labels at all. But it still naturally clustered similar digits together, just because, in the feature space, the same digits tend to have less variation between digits. There tends to be less variation within a digit than there is between different digits. So in the high dimensional feature space, the 64-dimensional feature space, digits that represent the same number tend to be similar, and so they tend to be clustered together. So this image shows the cluster center of every cluster. So you can see this cluster is probably a cluster of, 4s, but it probably has a few 6s in it too. This one seems to be a cluster of 3s. This one is probably a cluster of 1s, but maybe with some 7s mixed in. This one is most likely a cluster of 2s, but potentially also with 1s mixed in. This one is clearly a cluster of 9s, and so on. So we can see that the clustering algorithm naturally found the class groups from the data, even though we didn't explicitly ask it to do that. So this approach can be used more generally. If you have data that doesn't have class labels, you can use clustering, k-means, or potentially some better clustering algorithm to try and classify it into groups, even if you don't have those labels. Okay, so with these groups are actually ordered. So this is 0 group, 3 group, 0 group, 1 group, and so on. We want to kind of estimate how effective k-means was at finding clusters that correspond to single digits. And we can measure the effectiveness because we actually have class labels in this case. But the class labels are not in the same order as what k-means found, right? So k-means cluster 0 actually seems to correspond to cluster 4. So we're going to now kind of assign a label to each class, or to each cluster, sorry. So for each cluster, we're going to take the most common label of the samples in that cluster, and we'll call it the prediction for that cluster. Okay. So remember, this part of it is not unsupervised, because here we now actually have the labels. So describing exactly what digit it is, that's not the unsupervised part. But describing that, let's say, all of the points in a particular cluster belong to the same digit, that part was unsupervised. Okay, so the accuracy here is about 80%. So with 80% accuracy on this training data, we're able to find the correct grouping, meaning for 80% of digits, we're able to put them together with other digits of the same class, even without explicitly training for that. And here's the confusion matrix. So we can see that, let's say, 1s and 8s are often confused using this approach. So we have a lot of 8s in the 1 cluster and a lot of 1s in the 8 cluster. But other than that, most clusters tend to correspond well to a single group. Let's take a look at what happens. What do you think will happen if we try to find more than 10 clusters here? Let's see how it does. I'm going to ask it to find me 20 clusters. Okay, let's see. Did not give me 20 clusters. I mean, it did give me 20 clusters, but I'm not plotting them. Okay. So when I ask it to give me, let's say, more clusters, it might actually do a better job because it can potentially identify like different kind of models of different digits, right? So for example, it can now maybe distinguish between a one that's like a vertical straight line versus a one that has, the little line coming off the top. Or it can potentially have one cluster of sevens that has a crossbar and another cluster of sevens that doesn't have a crossbar. See, I'm not sure this code will, this code is not really designed for that. So I can't really measure the accuracy here. But generally speaking, we can see that this unsupervised approach can actually group together digits. It can group together digits that belong to the same class a lot of the time. Now we can also use we can try and visualize a cluster as a found. The clusters are in 64 dimensions, which we can't really visualize. But we're going to pass those 64 dimensional features to a kind of dimensionality reduction model, not one that we've learned about, but a different one. It's called TSNE. And we'll ask it to create more useful features of the data that we can use for visualization. TSNE is especially useful for, let's see, what did I miss? It's especially useful for visualizing clusters. I think I ran this out of order. All right, so TSNE is also available in sklearn. Okay, so I'm going to project the data into a different feature space. It's not exactly like PCA, so it's not necessarily a linear projection. But you can see that the projection of the data into the new space, and here we're coloring each data according to its class label. So we can see that the combination of k-means clustering and dimensionality reduction is able to very effectively group digits along with other digits belonging to the same class. And this was all using unsupervised learning. So the only thing here that's supervised about this is that we're coloring each cluster according to what we know is the true label, right? But we could just, not color it according to the true label, but just color it according to the cluster index. It would look exactly the same and it would be completely unsupervised. Now, there are actually many potential applications for clustering. So the one we've just looked at, which was a kind of unsupervised classification, is only one example. Another example is compression, okay, or dimensionality reduction, which is a kind of compression. So it's not often used for this particular application. So k-means is not the best way to do compression or the best way to do dimensionality reduction. But it's interesting to see how it could be used. So here's an example on an image. Okay, so this is an image. It's 427 by 640 by 3. Okay, and the last dimension is 3. That means there are 3 color channels in the image. There is a red channel, a green channel, and a blue channel. Now, one interesting thing you might notice, if you, let's say, plot all the pixels in the image along red and blue and red and green axes, right? So this shows you how the pixels in the image are distributed in the feature space. So do the pixels in the image cover the entire feature space of this color space? You could see that, among the entire range of colors that's possible, so 16 million possible colors, many colors are not present in the image at all, right? So these colors up here are not present in the image at all. Also, many of the colors are kind of very close together, right? So we have a lot of very similar pixels, so very small variations. And then we have a lot of potential colors that are not represented at all. So we could potentially reduce the dimensionality of the data by clustering the pixels by color. Okay, so kind of clustering the color space. So saying, okay, all of these pixels are similar color. Let's make them one cluster altogether. And then we'll actually just use the cluster mean for all of those. So instead of using 16 million possible colors, we'll use as many colors as their cluster means. And we can still actually represent the image pretty effectively doing that. So we're going to try this now. We're going to cluster it according to the color space. I'm using a mini batch k-means because we said k-means is pretty slow on high dimensional data. I'm going to use it to fit the data. Okay. So I already reshaped the data. So now each sample has, so now there are, let's see, 273,000 pixels. And each pixel has 3 values, a red, green, and blue. And now I'm clustering those pixels by their color value. And I'm going to now kind of assign each pixel to a color cluster. And I'm going to use the center of that color cluster for the entire cluster. So now if we look at the entire image, you can see here, instead of including all the small variations in the sky, for example, we've clustered pixels together by colors. So all of these pixels are now all part of one cluster, and we're representing them using the cluster mean. All of these pixels here are part of another cluster, again, represented using the cluster mean. So here we've reduced the dimensionality of the original image data so that we've done a kind of compression, so that now instead of needing 3 channels and 60 million possible colors to represent the image, we can now represent the entire image using only 16 colors, which can be represented much more compactly. Now, as I said, this is not the best way to do color compression. You wouldn't necessarily do it that way, but it's just interesting to see how you can potentially use this. Another more common approach to this would be to use k-means clustering to try and differentiate foreground background images. So let's try and reduce the number of clusters to 2. Okay, so if we use 2 clusters, for example, we can kind of distinguish between foreground or background. And we can do something similar with other numbers of clusters to try and group together different parts of the image. Now, this, of course, is assuming that parts of the image that are similar colors are otherwise like similar, which is, not necessarily generally the case. But it's just an example of the kind of things you can do with unsupervised learning. Even though you don't necessarily have a class label or you're not necessarily trying to learn a class label, you can use it to learn interesting things about the structure of the data or to do some interesting things with the data. Okay, any questions about clustering? Okay, let's move on to our next topic, which is dimensionality reduction. We just looked a little bit at k-means clustering on this handwritten digits data set. Let's look at what dimensionality reduction using PCA can do to it. So we're going to go ahead and load our full-sized MNIST. So with the 60,000 samples and 28 by 28 images. It takes a minute to load. Okay, so here's our original handwritten digits data. And we know that each image is represented by 784 pixels. So we're going to try and use PCA to project this data onto a smaller number of dimensions. I picked 40 out of a hat. This is the sklearn implementation of PCA, and I can use the fit, transform, and fit transform methods on it. And it also tells us some basic information about, let's say, how important each component is. This is really derived from the eigenvalue of each component, actually. So for each component, it tells me how much of the variance in these images is preserved by projection on the components, on that component. So we said, for example, let's look at our drawings from this week. When we looked at this earlier in the week, we said that PCA tries to choose as the first principal component the feature axis that maximizes the variance of the data. So this feature axis, as shown here. Then for the second principal component, it chooses the next axis that projection onto that axis has the second highest variance of all possible projections, and so on. So we expect that the first principal components preserve most of the variance of the data. And then as you produce more and more principal components, they're less and less informative about differences between data samples. So the first principal components explain most of the variance of the data. That's what we see here. So principal component number 1 explains 10% of the variance of the data. Principal component number 2 explains about 7% of the variance of the data. And that number decreases as we move along the principal components. Meanwhile, if we sum these numbers, right, we can see, for example, principal component 1 plus principal component 2 together represent 18% of the variance, and so on. And that goes back to what we said about reconstructing images from PCA. Okay, so when you reconstruct your images for, let's say, the first D coefficients, you reconstruct it using the first, some number of principal components. And so you care about how much of the total variance of data is represented by the first D principal components. Here we can see that the first 40 principal components represent together 80% of the variance of the image. Now we know that the image is 784 dimensional, right? So that means that the first 40 components together explain 80% of the variance in the image. And the last 744 components together only represent about 20% of the variance in the image. So most of the information in the image is included in the first principal components. Now I have here one of these interactive plots to help us understand what these principal components are and what they look like. Okay. So first of all, in addition to individual principal components, PCA will start by computing the mean of the image and removing the mean, right? So we said that the first step in PCA is center the image, so remove the mean. In our sklearn PCA, it starts by computing the mean. So that's what I'm showing you here. And it will remove the mean from the image before doing the projection onto the principal components. But of course, when we want to reconstruct the original image, we'll put the mean back in. So this is the original image. In this part here, I'm going to show you the reconstructed image using n components principal components. Okay. Here I'm using 0 principal components. So it's only showing the mean image. If you reconstruct the image using 0 principal components, you just have the mean image. On the bottom of this visualization, I'm going to show you for this particular sample, what is the magnitude of each principal component? Okay, what does that mean? Well, remember from here, right, that we reconstruct the image, or that we kind of decompose the image by computing this. So we compute V transpose times the mean removed image. Put that in a different color. Okay. When we, let's say, construct the image out of principal components, we compute this number, which is V transpose times the mean removed image. And this is a scalar quantity. And then we multiply that by the eigenvector, so the principal component. So when I say the magnitude of a particular principal component, I'm referring to this scalar quantity. And then on the other side of this visualization, over here, so this shows the magnitude, and this shows that actual principal component vector. So remember, each principal component vector is, let's say, 64 dimensional in this, 784 dimensional in this case, because the data is 784 dimensional. So I have 40 of these vectors. I'm going to show you for each principal component, I'm going to show you the actual vector here. And in this image, I'm going to show you the magnitude of that principal component. And then up here, I'm showing you the reconstructed image using D principal components. So let's just review what this visualization shows us. This is in the bottom left of the image. This is in the bottom right. This entire quantity is in the top right. So the reconstruction using the first D principal components. And then this, the original image, is in the top left. So that's what all these panels of this visualization will show you. All right, so let's walk through it. Okay, so first off, we have just the mean of the image, and I'm representing 0 principal components, so just the mean. Now I'm going to add the first principal components. So let's set n components to 1. Okay. So this is principal component, the first principal component times the magnitude, right? So for this particular sample, the magnitude of the first principal component is large. Now, looking at this principal component, it's very easy to see why. So this principal component is a vector that says, let's say, you should have writing in this part of the image that's inside this green space. And this part of the image that's black should have no writing in it. Okay. So it's kind of very easy to see how an image that's a 0 can be reconstructed by saying, okay, give me 10 times this principal component. So for image data, the principal components represent like building blocks of the image. Instead of having individual pixels, you can think of it as like, templates of groups of pixels that we combine to reconstruct the original image. So here's principal component 0, the first principal component, and its magnitude. And here's a reconstructed image using the first principal component. Okay, let's look at what happens when we add the next principal component. Okay. The next principal component looks like this. Okay. Is this principal component an important part of this image? Well, it's not nearly as important as the first principal component. So the magnitude is, relatively much smaller, which means in order to recreate this original image, you take a lot of principal component 0, but much less of principal component 1. And here's a reconstructed image so far using the mean and principal components 0 to 1. All right, the next principal component looks like this. Okay, this one is considered much more important for this particular image. Okay, so you can see the magnitude is greater, it's close to 3. And here is a reconstructed image using the mean plus those first three principal components. Okay. And as we continue, we can see that we're constructing a more and more accurate copy of the original image by adding scaled versions of these principal components until eventually we end up with something like this, okay, which is pretty close. Let's look at what happens with a different digit. So I'm going to pick a different sample. Okay, so here's a 3. 3 is a good example. Okay, so here's a 3 with the mean image. So this is a reconstruction using none of the principal components, just the mean. Okay, this is principal component 0. Does it contribute a lot to the image 3? So the answer is no. So this image is not very useful or helpful for reconstructing the 3. Okay. So you can see the magnitude is relatively small. And here's a reconstructed image using the mean image plus this principal component. It's not very close because this principal component is not very useful for reconstructing the 3. Let's look at the next one. The next one is somewhat more useful. So this principal component is kind of a combination of many different images. So it says, let's say, have some writing here where it's white, have no writing here where it's black. So this helps us construct this particular 3 a little bit more. And the next principal component is also more helpful. So you can see it says, have some writing over here. You can see it's kind of vaguely 3 shaped. So it's definitely very relevant to 3, but it's not specific to 3s. So other numbers are also going to benefit from this. So for example, you can also see how a 9 shape like this would also benefit from being reconstructed by this. For this particular sample, the most important principal component seems to be number 7. Okay. So looking at this principal component, number 7 kind of defines this empty space here and this empty space here. And that turns out to be very helpful for creating this outline of this 3. So you can see how the principal components are like templates or building blocks that can be used to reconstruct the original image. Here's this 3 reconstructed from 40 principal components. So you can see it's a pretty good reproduction. Let's look at another example. I'm looking for 1. Okay, so here's a 1. So this one is interesting in particular because remember just a moment ago, right, we looked at a 0 and we said that for a 0, it will have a very large positive magnitude for principal component 0, because principal component 0 says this space should have writing in it and this space should not have writing in it. Okay. Now this principal component is also very helpful for 1s, but in the opposite case, right? So for 1, we want to have writing in the center and we want to have no writing outside of the center. So if we look at a sample that's a 1, you can see principal component 0 is also very helpful for producing a 1. It just has a very large negative magnitude instead of a large positive magnitude. So if we were mapping, for example, the entire set of 0s and 1s along the axis of principal component 0, we'd expect to have a large cluster of 1s, a large cluster of 0s around here. I'm drawing a second axis just so that we can kind of jitter these, but so if we are mapping this data according to principal component 0, we'd expect to see kind of the 0s far along the positive side along the principal component 0 axis. The 1s would be far along the negative side along the principal component axis. And for some digits where principal component 0 doesn't matter as much, we might see more examples in the middle, right? So we'd have a small magnitude of principal component 0. Let's see if we can find some others where principal component 0 matters. So you can see for a 4 or a 5, principal component 0 doesn't matter too much. But for a 1, it always has a very large negative magnitude. And for a 0, it will usually have a large positive magnitude. Let's try and visualize this ourselves. So we can't really visualize it in 40 dimensions, obviously, but we can visualize the first 3 dimensions, which together explain 1, 2, 3, about 25% of the variance in the data is explained by the first 3 principal components. So we're going to visualize the data in 3D, just this subset of the data. And since we happen to have the class labels, we can color the data according to their class labels. So first of all, notice along the principal axis, along the principal component 0 axis, right, we do indeed see that all the zeros, right? So this blue color shows all the 0 samples. The zeros all tend to have a large positive value for principal component 0, because principal component 0 is very helpful for reconstructing zeros. Principal component 1 tends to have a large negative value along the principal component 0 axis. That's a PC0 axis. Because the inverse of principal component 0 is helpful for constructing a 1. But these other digits in the middle, which tend to have a smaller value for the magnitude of principal component 0, for these digits, principal component 0 is not especially helpful for reconstruction. Then we have some other digits like 9, for example. So some 9s are more like a 1, and for those 9s, principal component 0 is very helpful. But for some 9s, principal component 0 is not helpful. And we can imagine what those 9s might look like, right? So if you have a 9 that looks like this, right, the principal component that says have writing in the middle of the image but not outside, that's very helpful. But if you have a 9 that looks like this, you could see how it would be less helpful. So then we'd have this magnitude of 0 or close to 0. Let's look at some of the other first 3 principal components. Let's rotate a little bit. Okay, so here you can see more clearly that, you know, the 1s are all on the positive side, negative side of PC0. The 0s are on the negative side. Let's look at PC1, if we can. Where's PC1? Okay, so here's the PC1 axis. Looking at PC1, we can see that it's helpful for some 3s. So some 3s use the kind of inverse of PC1. And some 9s tend to use have a positive magnitude for PC1. So some 9s and also some 4s. Looking at PC1, let's see if we can understand how it affects 9s and 3s. I'm going to find a 3. Okay. So here's a 3, and we're looking at PC1. So this is PC1. And you can very clearly see here how PC1 can be helpful for reconstructing 9s and 3s. So PC1 says, you know, have writing in this image, in this part where it's white, don't have writing where it's black. So, you know, we can see that the 9s tend to have a large positive value for PC1. Right? So for a 9, they do actually often have writing here and no writing here. For a 3, it tends to be the opposite. So for a 3, let's see. So for a 3, we tend to want the inverse of this to reconstruct the image. And so we have a large negative value for PC1. And finally, let's look at PC2 here. Turn this a little. Okay, so here's PC2. Trying to get a good view of the PC2 dimension. Okay, so here's a slightly better view of PC2. PC2 is a little bit harder to understand. We can see that PC2 tends to be useful for some specific images, some specific digits, not as useful for other digits. And there doesn't seem to be necessarily an obvious trend in what digits are separated by PC2. So PC2 is still a very important component. Let's look at it. This is PC0, this is PC1, this is PC2. This is PC0, PC1, PC2. Okay, so PC2 is very important because it's a third principal component. It explains a lot of the variance in the images. But looking at this, we can see it doesn't necessarily explain the variance in the images that's in variance between classes. Right? So PC2 represents something that makes images different from each other, but not necessarily something that makes one type of handwritten digit different from another class of handwritten digit. It's just something that makes, individual digits different. And it could be something that makes individual digits within the same class different. Looking here, you can kind of see that it might be like a rough representation of whether the digit is leaning forward or backward. So if the digit is leaning forward, right, maybe we'll have a positive value here. If the digit tends to lean backward, you could see we're more likely to have the inverse of this. So maybe then we'll have a negative value. Let's look at a few examples to see if that holds up. Okay. Yeah. So here's like, let's say an image, a 7 with a strong lean backwards. Here's the 3 with a lean forward. So you can see the 7 with the lean backwards has a positive value for this PC, because there is writing in this part. The 3 with a lean forward has a negative value for this PC. So the principal components represent something kind of fundamental about the different images. It's not necessarily something that makes one class different from another class. We're not training it with any information about the class differences. And sometimes, so here you can see that principal component 2, which is very important, really just encodes whether the image is leaning forward or backwards, or is standing straight up. Right? So it represents differences between images, but not necessarily interclass differences. Okay, I think that's all for the handwritten digits. Any other questions? We're going to look at a more complicated example of dimensionality reduction. So we just looked at dimensionality reduction on MNIST, which is relatively simple data. Now we're going to take a look at our rock, paper, scissors data. So we worked with the rock, paper, scissors data last week when we practiced fine-tuning a classifier to learn this data. Now we're going to work with a slightly different version of the data. So with this version of the data, we've done some image pre-processing so that we remove the white background from each image, and we've also converted it to grayscale. So now our images look something like this. So they're 200 by 300 pixels and remove background, and we've converted to grayscale. And then we have a label that represents whether it's rock, paper, or scissors. Now let's see what PCA makes of this data set. So again, we're going to ask it to find the first 40 principal components. And then we'll look at the proportion of variance explained by each principal component. So we see that again, almost 25% of the variance in the data is explained by the first principal component. And cumulatively, 40 principal components represent something like 80% of the total variance. This is the mean image. Sorry, no, this is actually the first principal component. This is the mean image. So we know that PCA removes the mean first, and then when we're reconstructing, we add that mean back in. And here's the 40 principal components. Now we expect that the first principal components are kind of more fundamental because though they're explaining the most variance of the image. And the later principal components are maybe more fine details. And that's what we see here. So you can see that the first principal components sort of represent the fundamental position of the hand within the image, right? Some of them have a hand up here, some of them have a hand down here, right? So depending on where the hand is located in the image, that's like the first and most kind of highly varying thing between the images. So that's what's encoded by the first few principal components. But then the next principal components start to represent something that's more about the position of the fingers on the hand. So the first principal components represent the position of the hand in the image. The later ones start to represent the position of the fingers. So they're making a scissors motion. We can encode both the position of the fingers and the position of the space between fingers. Are we making a scissors motion, a rock motion, a paper motion? We can kind of encode knuckles. So you can see the knuckles on the hand are encoded by some of the principal components. And as we increase the index, you can see these principal components encode much finer details and explain a smaller proportion of the variance in the image. Let's do the same exercise with the interactive visualization. Okay, so just like before, we can reconstruct the image from the principal components. In sklearn, we use inverse transform to do that. So if let's say XPCA is a transformed data, inverse transform is reconstructed images. And we'll do the same interactive game to represent the images. Okay, so once again, we're back here and we're going to represent, just remind you again. Okay, so this quantity is going to be on the top left. This is the original image. It's not actually the mean removed image on the top left. It's just the original image on the top left. Okay, this quantity, the reconstructed image, is going to be on the top right. Then for each individual principal component, right, we'll look at the magnitude of the principal component. This is on the bottom left. And we'll look at that specific projection. So this part, not the sum, but just the part inside the sum, is going to be on the bottom right. Okay. So here's, let's say, an original image and the mean. Let's look at the first principal component. Okay, so the first principal component kind of encodes where the hand is in the image. Right. Let's look at a few other examples of images and see how the magnitude of that first principal component changes. Okay, so you can see if the image is if the hand is near the top of the image, well, this principal component says we have kind of image data at the top and we don't have image data. This principal component says we don't have image data at the top and we do have at the bottom. So if the hand is at the top, we'll have a strong negative magnitude for this. If the hand is at the bottom, we expect to have a strong positive magnitude for this. Okay. And so that's what we see. So this encodes the position of the hand, right? If it's strongly at the top of the image, we have a large negative magnitude for this component. If it's in the middle, we kind of have a smaller magnitude. And if it's strongly on the bottom of the image, we have a large positive magnitude. So the first principal component tells us where the hand is in the image. Second principal component looks like it also tells us something about the position of the hand in the image. So let's look at more examples. Let's see if we can find out what the trend is. Okay. So I believe this one will kind of encode the position along the horizontal axis that the hand includes. You can see for hands that are mainly in the right side of the image, the magnitude of this principal component tends to be negative. For hands that have more contribution in the left side of the image, right, you could see the magnitude is larger. So this principal component basically encodes whether there's a hand in this part of the image or not. Now, this is probably also kind of roughly related to class. So I think these are sorted, by the way. Let's look at some in the middle. Let's look at some samples in the middle. Right. So looking at, let's say, the paper images are more likely to have, fingers on the left side of the image. So I would expect that the paper images are more likely to have a large positive magnitude for principal component 1. But of course, the farther it is towards the left, the larger that magnitude. So we still have some paper images that are more towards the right, and these will still have a small magnitude or a negative magnitude. Okay, and let's look at rock, paper, scissors. Okay, and we have something similar with scissors, where if the scissors gesture is farther towards the left of the image, we're more likely to have a large magnitude or positive magnitude for PC1. Okay, the next principal component encodes the position of the fingers here. So this principal component encodes whether there are kind of fingers stuck out in the hand. Okay. So we can see this rock example has a kind of small magnitude here. Let's look at some paper examples. Okay. So the paper examples tend to have a negative or positive magnitude here, depending on the position of the fingers. If you have the fingers together in the paper gesture, then this principal component is less relevant. But I expect in some of the paper examples where the fingers are spread out more, let's see if we could find one, right? Then this should be more relevant because this image encodes both fingers spread out, but also space between fingers. Let's look at what this principal component does for the scissors. So for the scissors, we can see these tend to have a larger magnitude for this because this really very specifically encodes kind of the inverse of having two fingers spread out. But of course, it all still depends on the position of the hand within the image. So here, because the images can be much more complicated, depending on where the hand is in the image, right? So sometimes this principal component will be responsible for encoding, let's say, space between fingers. Sometimes this principal component will be responsible for it. Because there's so much variance in where the hand is in the image, we need more principal components to encode these differences. Okay, let's look at an example of a more fully reconstructed image. So here you can see the reconstructed image from 40 principal components. So it's a pretty good representation of the original image. We don't have obviously all the finer details, the variation in kind of skin tone, but we can definitely very clearly see, the gesture. Just as with the digits, we can use this to kind of visualize the data. So it's a little more difficult to see just because these principal components don't necessarily encode differences between classes. some of what they encode is differences between samples of the same class. But we can still see, for example, so some variation between classes along these principal component axes. For example, we previously said that the paper gesture is more likely to have writing in this part of the image. So principal component 1 becomes much more important for the paper gesture. So we can see some measure of that here. Now, one of the things we can do with reduced dimension data is we can use it to then do some supervised learning. So if we would try to do supervised learning on this 784 dimensional data set, it might not do very well. But if we try to do supervised learning on the lower dimension data set, we have more flexibility because we can use models that don't do well with high dimensional data, or that, let's say, don't do well on data with many irrelevant features. Now, I'm not running this in real time because it's a little slow. You'll see why in a moment. But I'm going to take this data set, so the original data set, not the PCA data set, and I'm going to split it up into a training and a test set. And I'm going to use a pipeline, which is a sklearn feature, to define a two-stage machine learning process. What are the two stages? The first stage is going to be take the data and pass it to PCA. And the second stage is going to be take the PCA transformed data and pass it to a support vector classifier with an RBF kernel. So I'm going to do some machine learning in two stages. First stage is use PCA to learn a new feature representation in lower dimension. The second stage will be use a support vector machine with an RBF kernel to learn the class labels. Okay. Now we know that support vector machines are very sensitive to the hyperparameters. PCA is also somewhat sensitive to the hyperparameters. So depending on, there's a kind of interaction between the PCA and the support vector machine, right? So we want to tune the hyperparameters of the entire pipeline altogether. What do I mean by that? Well, it's very possible that, we might just, let's say, choose some number of principal components that we think are appropriate. But then those might not be the most appropriate principal component numbers for the particular support vector machine hyperparameters we chose. So since all of these hyperparameters, the number of principal components, the gamma of the RBF kernel, and the C of the support vector machine classifier all affect the result of the classification, we want to tune them all together. Now, we've previously looked at doing this using grid search. So we looked at using a grid search in sklearn to search over a particular range of parameters and find the optimal hyperparameters among those using cross-validation. And that took a really long time. So when we did this ourselves, we first, let's say, defined a particular range of hyperparameters, and then we looked at the result to decide whether we should expand that range or search other areas within the range. It was a complicated process and it took a long time. In this example, I'm using a different type of hyperparameter search called a Bayes search. I'll briefly describe what that does. So what this does is, okay, so I do still have to define the range of values I want to search. Okay, so I'm going to say search among PCA number of components between 20 and 100. And for my classifier that I defined, search gamma values between 0.0001 to 0.01. And for C values, search from 1 to 3000. But unlike the grid search, I'm not going to specify that I want to search, let's say, only those two values, or I'm not going to specify that I want to search only a list of values. Instead, I'm going to tell it to do the following. I'm going to say, okay, so start with, let's say, maybe the extreme points in this hyperparameter space, and then use information from the previous hyperparameters to decide where to look next. So here's a little bit of a visualization of this process. Okay. So let's say this is the entire contour of the loss space for a particular problem. Right? So the optimal hyperparameters are going to be maybe somewhere along here in this space. Okay. So with a Bayes search cross-validation, okay, so we start off by sampling a few points at the extreme cases. And based on what we've sampled so far, you can see in the bottom image here, the Bayes search is building up its kind of internal estimate of the loss surface as a function of the hyperparameters. And how does it build up its estimate of the loss surface? Well, each point it samples gives it more information about the loss surface, but also each point that it samples gives it more information about what would be the best place to sample next. So it iteratively decides which hyperparameter combinations to try based on what the result was for previous hyperparameter combinations. Now, I'm not going to do this live now, okay, but you can see, let's look up here. So I'm using 5-fold cross-validation. You could see it starts by kind of sampling some values that are maybe a little bit all over the place. So first it samples, let's say, 23 principal components, gamma of 0.005, C of, let's say, 69. In the next iteration, you can see it changes C a lot from 69 to 2. But then in later iterations, now it's changing PCA number of components a lot. So now it's looking at maybe a much larger number of components, but a smaller value of gamma. So it's sampling different points in the hyperparameter space, and it's progressively learning what are the best parts to sample, okay, as it does this. Eventually, it tells us that the best hyperparameters are C is 7, gamma is 0.0005, and a small number of components, so n components 22. And the score, so the accuracy of the classification on the training set is 98%. The accuracy of the classification on the test set is 96%. That's actually really good. We previously did this same type of classification using a fine-tuned neural network. That was a much more complicated model, right? Much more expensive model to train. And that also gave us accuracy in the 90s. Now, we didn't do it this summer, but in the past, I've assigned a homework assignment to try and train a convolutional neural network on this data set. It's actually really challenging to train a ConvNet on this data set and get good accuracy from scratch. It's a lot easier if you're fine-tuning, but if you're doing it from scratch, much more difficult. This approach actually gets really good performance, and it's much less expensive and much less fragile to train. So this shows us that, oh, and here's a confusion matrix. So you could see, sometimes it mixes up paper with scissors. That's kind of to be expected, right? Sometimes it mixes up rock and paper, but overall it does a really good job. So that's pretty impressive for, considering that this is purely a linear method, a linear PCA, actually nonlinear support vector classifier. But also very impressive considering we're not doing any data augmentation. We're not doing all the normal tricks we need for neural networks. The PCA does a very good job of pulling out the best features of the image and feeding them to a supervised classifier. Now, you might be thinking that what the PCA did, learning some representation of the image, is very similar to what the first part of a neural network does. So when we learned about neural networks, find those drawings. when we learned about neural networks, we said the first parts of a neural network are learning a representation of the features that's more helpful for classification than the original features. And then the last stage of a neural network does something similar to the support vector machine in this example. It takes those learned features and then does classification. So what we just did with PCA and a support vector machine was kind of a similar idea. We use a PCA to learn a better feature representation, a more informative feature representation. And then we use a support vector machine for classification. We could actually use a neural network for the first part. So we know that neural networks are great at learning features. In some cases, they're even better than PCA because they can learn nonlinear representations of features. So we can use a neural network with, let's say, a feature learning part and another part. What's the other part? Well, we're going to use an autoencoder. Let's find our autoencoder. Okay, so we're going to use an autoencoder, which does a feature learning part, and then a decoder, which tries to take the reduced representation of the data and reconstruct the original data. We can use this to do what PCA did, to do the dimensionality reduction. So let's look at an example of this. In order to do that part, I'm going to change my runtime to GPU. Wait for my GPU. Okay. I'm going to get the TensorFlow format of the data set again. Okay. And I'm just putting it into NumPy format because we're more comfortable with it. Okay, let's look at the model we built up. So I'm going to build the model in two stages. I'm going to build an encoder, and then I'm going to build a decoder. Okay, the encoder is going to start with an input shape of 224, 2243. That's the dimensionality of the data. Okay. I'm going to start with, let's say, 16 convolutional filters in the first stage, but I'm going to follow them with a pooling layer. So my convolutional filters are going to use padding. So when we do padding equals same for a convolutional layer, we don't reduce the dimensionality of the image, but the pooling layer reduces dimensionality. Okay. So I'll have a convolutional layer followed by an activation function. The output shape of this is going to be 224 by 224 by 16, 16 because there are 16 filters. But my pooling layer will have that size. Okay, so after the pooling layer, the dimensions are 112 by 112 by 16. Then I'll do another convolutional stage, but with a smaller number of filters, so 8 filters. Okay, and again, I'll use a ReLU activation, a nonlinear activation function. I'm just going to run the rest. Okay, and then I have another pooling layer, which again reduces the dimensionality by half. And finally, I'll have a third convolutional layer with only one filter. Okay, and that's also going to be followed with a pooling layer. So the output of the encoder is going to be 28 by 28 by 1. Okay, so I've reduced the dimensionality from 224 times 224 times 3 per image to 28 by 28 by 1 per image. Now the decoder is going to be the same structure in the reverse direction. So the input to the decoder is going to be the output of the encoder, 28 by 28 by 1. And then I'll follow that up with an upsampling layer. So this kind of does the opposite of max pooling. Instead of decreasing the dimensionality, it increases the dimensionality. So I'm increasing the output shape with each, let's say, set of convolutional activation and upsampling layers until eventually the output shape is kind of the inverse of the encoder. So you can think of it as like encoder, decoder. Now the output of a decoder, well, the width and height of each filter is the same as the original image, but I have 16 filters there. And we know my original image has only 3 channels. So when I put this together, I'm going to create a model where I take the encoder, stack the decoder on top of it, and then I'll just stack one more convolutional layer on top that has 3 filters, just because the original input images were 24 by 24 by 3. So my eventual output size is going to be 24 by 24 by 3, just like the original input. Okay, so I'm in the middle of training this model now. Let's see what it produces. It's going to take maybe another minute. Notice that when I train the model, so normally when we call model fit on a neural network, we pass the feature data and then we pass the labels. Here, the labels are the feature data itself. So we're training this network to kind of learn to reconstruct the original input image as the output. So when we call fit, we pass the feature data and the feature data again. Same deal for the test data. So here we're not using the validation data for early stopping or anything like that. So it's okay to use the test data. And you could see again, both the input and output of the network should be the same because we're asking the network to learn the identity function, but with a bottleneck in the middle. Okay. You can see the loss is starting to stabilize a little bit. Okay, and remember the loss that it's optimizing here is the reconstruction loss. So the distance between the input, which is, let's say, the true label, and the output from the reconstructed features. Okay. So we can get the kind of decoded images, so the output of the entire model by calling predict on the model. But we can also find out the encoded images, so that latent representation in the middle, by calling predict on just the encoder. Okay. So we're going to do that now, and it's going to tell us the encoded images shape. Those should be just 28 by 28 by 1 per sample, because this encoded representation is of smaller dimension. Okay, so we have 300 test images, each 28 by 28 by 1. Here's a visualization. So on the top, we have the original images. In the middle, we have the encoded images. So this is the representation produced by the neural network. That's 28 by 28 by 1. And then at the output, we have the reconstructed images. So we can see it did a pretty good job of learning the reconstructed images. It's a little different from the PCA. It seems to have been learning like edges. So you can see it's sort of learning where the edges of the hands are in the image, which is an interesting thing to learn. But we can see that just like PCA, it's able to kind of effectively reproduce the original image from a much smaller intermediate representation. Okay, that's all I have for today. Are there any questions? Okay. I also just want to remind you that we have on the calendar, starting this week already, we have some extra review sessions that you're welcome to attend as you're preparing for the exam. So you can come, bring any questions you have. If nobody comes to them, or if there are no questions, I'm just going to stop the session early. But the first of these starts tomorrow. So feel free to come and bring any questions or anything you might want to review in more detail ahead of the exam. All right. Thanks a lot, everybody.